Welcome to The Explainer. Today, we're diving straight into a truly fascinating gap. I mean, think about the massive divide between the artificial intelligence that lives on our screens and the physical robots actually trying to operate in our real world. We've all seen the massive leaps in AI lately, right? But when it comes to physical space, well, the story is incredibly different.
It brings up this highly relatable, honestly kind of funny frustration. Why is AI writing award-winning poetry but utterly failing to fold a simple basket of laundry? We're seeing artificial intelligence do incredible, borderline magical things digitally, yet when physical robots have to actually move through our homes, they remain surprisingly clunky and limited. So what's really going on here? The core of the problem lies in a severe contrast between two very different fields. Language AI, it scales at lightning speed because internet text data is practically endless. But robotics AI, it is starving for real-world physical data, and it's strictly constrained by the actual unbreakable laws of physics and gravity.
Which leads us straight into the physical data bottleneck. Collecting robotic data in physical reality is dangerously slow, and it's incredibly expensive. If you want a robot to learn how to just pick up a cup, you literally have to watch it try, fail, and try again in real time. You can't just hit fast forward on physical reality. So to solve this massive data bottleneck, pioneers like Fei-Fei Li over at World Labs are building the next frontier of AI. They call it spatial intelligence. This isn't just about reading text on a screen anymore. It's about giving machines the ability to generate, comprehend, reason with, and actually interact with 3D spaces, both in virtual environments and out in the physical world. And this really highlights our own biological advantage. As Fei-Fei Li points out, humans do something called counterfactual reasoning. Just like an athlete visualizing a soccer game in their head to prepare for any scenario, robots desperately need a way to simulate and play out actions they haven't physically performed yet. Humans do this naturally, but robots need a system built specifically for it.
Right, so this brings us to an ultimate solution pioneered by Yunju Li and his team at Scenix. They are essentially bypassing the slow physical world altogether by building a sort of matrix for robots to learn inside. It's called the real-to-sim-to-real pipeline, and it completely changes the game for how machines acquire physical knowledge.
Let's break down how this actually works. It happens in 3 distinct steps. First, we scan and map a real physical environment into a digital clone. Second, we train the robot inside that hyper-fast digital simulation, randomizing all sorts of variables. And finally, we take that fully trained brain and drop it reliably right back into the physical machine. The benefits of doing this inside a simulation are absolutely massive. We gain ultimate controllability, introducing systematic randomization. That means infinite variations of lighting, object geometry, and friction to give the robot total coverage of every possible scenario. And the best part? It's completely unbound by human operating speed. A robot can run thousands of safe tests without ever breaking a single piece of expensive hardware. When you stack these two approaches up against each other, the difference is just staggering. Physical, real-world teleoperation relies on human operators guiding a robot, which is actually slower than normal human speed and heavily limited by physical hardware constraints. But with simulation training, you get systematic, massive speedups. You can test in parallel, gathering lifetimes of data in mere hours, simply because you're no longer fighting gravity. Central to this entire digital training ground is a base model codenamed Marble, developed by World Labs. Marble is essentially a generative engine. You give it a simple image or a text prompt, and it magically generates these geometrically consistent 3D interactive environments. It literally builds the highly accurate digital world where the robots go to practice. And this is exactly where the merger of World Labs and Scenix creates the perfect infrastructure. World Labs brings the generative sparse 3D reconstruction, like Marble, while Scenix brings the hard physics simulation, the real-to-sim pipeline, and the robotics evaluation. The result of bringing them together? A perfectly consistent, physics-aligned world built specifically to solve the robotics data drought. Okay, so this leads us to the next evolution, the omni-model future. We're moving past AI models that simply spit out pretty video pixels. The future foundation models for robotics will be omni-models. That means they take in multimodal inputs like vision, depth, and text, but crucially, their actual output is physical action in the real world. Yunju Li points out exactly why these physical actions and rules matter so much. If a robot pushes an object in a standard video prediction model, the object might just magically disappear because the model doesn't actually understand physics. A true robotics omni-model has to act as a forward simulator that understands real physical consistency, not just surface-level visuals. This creates what we call the data flywheel. We start by heavily relying on hard physics rules in simulation to ensure consistency. We train the robot policies there, then deploy them into reality to collect new, real-world physical data. As that data cycles back into the system, the environment models transition from strict physics to becoming incredibly smart through actual learning. But wait, all of this raises a massive question, and it's one that is highly overlooked in the robotics industry. How do we actually evaluate if a robot is getting smarter without waiting years to test it? I mean, if you make a software tweak, you need to know immediately if it worked, right? Think about real-world evaluation. It relies entirely on physical wall clock time. Trying to figure out if a software tweak improved accuracy from 90% to 92% takes an absolute eternity in the physical world, not to mention it can be dangerous. But with simulation evaluation, because it is perfectly aligned with real-world physics, companies can run thousands of scalable, safe tests instantly. The ethos behind all this incredible technology is actually surprisingly grounded. As Yeonju Lee notes, his North Star is making robots work in real environments today. This explainer isn't about some distant science fiction future where robots take over the world. It is a highly pragmatic, business-focused mission to automate dull, dirty, and dangerous tasks for real clients immediately. Which brings us to a realistic timeline for where these robots will actually go. Fully structured environments like car factories, they've had automation for decades. Right now, the immediate, sustainable focus is mastering semi-structured environments, places like warehouses, electronics assembly, and labs. The grand challenge, which is still much further out, is the unstructured environment. A messy home with kids and pets is literally the absolute hardest place for a robot to navigate. What makes World Labs' approach so unique is that they aren't trying to build the physical metal chassis of the robot. They're building an embodiment-agnostic platform. Think of it as a universal digital brain gem that can train any hardware, whether a company's building a single robotic arm, a mobile base, or a four-legged quadruped. Now, as we look to the future, we do have to maintain what Fei-Fei Li calls measured optimism. Just think about this number for a second. 30 watts. That is the unbelievable power-to-performance efficiency of the human brain as it seamlessly navigates 3D space. Getting a robotic system to match that kind of efficiency in unstructured physical reality is still a very, very long way off. But as these generative 3D virtual labs come online and that massive physical data bottleneck finally shatters, we really have to ask ourselves, how fast will physical robots advance now that they are no longer constrained by the slow speed of physical reality? Are we about to witness the same explosive, world-changing scale in robotics that we just saw in language AI? I'll leave you to think about that. Thanks for joining me on this explainer.